now we're recording. Okay. And hopefully this recording will continue throughout the entire evening while I'm actually lecturing and not cut off halfway through. So chapter 3, ions, ionic bonds, etc. That's what we talked about last week. So therefore, I'm not going to focus on that a lot. I've already babbled on enough about that as it is. But a couple of things. Do remember that ions are charged particles. Do remember that cations, therefore, are positively charged. Please know that anions, therefore, are the counterpart of cations and are negatively charged. Okay. So this means charged particles, essentially charged atoms. Cations are positively charged due to loss of electrons, and therefore number of electrons being less than number of protons, and you cannot change the number of protons in the nucleus, nor can you change the number of neutrons. But charged particles, you cannot change the number of protons. The only thing you can do is change the number of electrons surrounding that nucleus. In comparison, therefore, anions are negatively charged due to a gain of electrons. Therefore, the number of electrons now exceeds the number of protons in the nucleus that the electrons are surrounding. Okay. Any questions about these topics so far? Any questions? Question? Oh, it says charged atoms. That's a very good question. That looks like a prescription signature. Classic joke, right? Doctors can't actually write clearly. But as you see, if I take the time to, I can actually write clearly. That's why they wouldn't let me into med school. Okay. Good so far? All right. Any other questions? Okay. So next, we've defined ions, types of ions, etc. What is an actual ionic? Okay. One other thing, therefore. Cations lose electrons. Anions gain electrons. And how does that happen? The formation is driven by electron transfer from the atom losing the electron to the atom gaining the electron. And the classic example of that you'll have seen in your book is something like sodium, and you bring it into contact with chlorine. Sodium has 1 valence electron. We're going to use Lewis dot structures frequently here to show and indicate number of valence electrons. I'll define those for you briefly. A Lewis dot structure, if you have not absorbed yet, is literally the chemical element symbol surrounded by the number of valence electrons. And you do that by putting 1 electron on each side to begin with. And then you double down and go 1, 2, you're 1, 1, 1, 2, 2, 2, 2, so on and so forth as you need to. But there should never, in general, be more than 2 electrons or a pair of electrons to a side, because what does each side represent? Well, here I come answering my own question. Each side represents an orbital. Okay. And so therefore you cannot have more than a pair of electrons in an orbital. So chlorine has how many valence electrons? Look at your periodic table for a second. Recall from last week if you need to. Looking at chlorine, chlorine is right here. Group 7 on the main groups, ignoring the transition elements. the main groups, group 7 means it has, starting with a neutral atom, therefore it has 7 valence electrons. Group 7 translates to 7 valence electrons. So therefore I've got 1, 1, 1, 1, 1, 4, 5, 6, and 7. Okay. By that same token, why does sodium have a single dot? Well, it's in group 1 right there. 1 valence electron. Okay. Now, sodium is going to become the sodium cation. So therefore, this electron is going to move over here and transfer to chlorine. And that is how you end up with the ever so classic sodium cation, which now has it actually has a complete octet. If you were to look at the sodium atom, it actually has a complete octet, but it has 1 less electron than number of protons, and therefore it has a positive charge. Chlorine, on the other hand, has now gained an electron, so now its structure, or I should say its symbol, looks like this with a complete octet. We put brackets around it to indicate that it is an ion, and we put a charge like so. Ions get brackets and charges like so. Okay. Now, questions? Typically, we would actually put the charge. That's a good question. We would typically put the charge on the outside of the bracket, I would say. Yes. You indicate the charge on the outside of the bracket, because on the inside of the bracket would be the electrons. Yeah. Now, this becomes even more important when we talk about polyatomic ions. Okay. What else, guys? What other questions might you have? Okay, if there aren't other questions, then I will now continue. So, does this make sense to you guys? Key thing I want to show you is full transfer of an electron, okay? So, that means, in general, ion formation involves full, complete transfer of electrons, okay? Ion formation means an electron is literally plucked off one atom and thrown onto another. It's a violent thing. You rip that electron away from one atom and stick it onto another. Well, that last part doesn't sound that violent. And it is favorable. It is energetically favorable for this to happen, even though by itself it is not favorable for the sodium atom to lose its 1 valence electron. Sitting in a vacuum, sodium will not let go of that valence electron. But if you put it next to a chlorine atom, it is now energetically favorable, and that's driven by the fact that if you were to do the math, the energy of that chlorine atom becomes so much more stable that it drives the loss of that electron from the sodium atom. That's not math we're going to have to worry about. I just want you to understand that these things can't be separated from each other. You cannot generally generate ions in a vacuum, generally. Okay. Make sense so far? At all? Okay. Cool. So that's ion formation. Ionic bonds are even easier to think about, really. Ionic bonds, in general, are formed between atoms of opposite charge. So positive and negative attracted toward one another. Ionic forces are strong. They pull toward one another. These are very strong forces. Okay. The ionic bonds are quite strong, and therefore most ionic compounds tend to be solid at room temperature. Okay, at room temperature, which is what we care about. A lot of these things have such high melting points, you're not going to sit in a room with sodium chloride and melt it and sit in that room at the same time in general. Not at least without an isolating device that keeps the heat away from your body, because you could also melt your own body utilizing the heat needed to melt a lot of these ionic compounds. Okay. Now, if you're thinking about what happens when I throw sodium chloride into water, that's a whole other story. We're just talking about taking pure ionic compound and melting it without the interference of any other compound. Okay, we're talking about pure ionic compounds being melted with heat. That takes a lot of heat. Okay, good so far. Okay, so there's a couple of things that I want you guys to take away from all that blah blah blah. Ionic compounds, full electron transfer between atoms to form ions. That happens before the formation of the actual ionic bond. You first transfer the electron from one atom to another atom to form the ions. Once the ions form, then you have the charges that then are attracted to each other to form the ionic bond. Okay? Does that make sense? Ions must first exist to be able to form a bond, and you must therefore actually go through the transfer of the electron or electrons to be able to form those ions. Okay? All right. Now, in chapter 3, I believe there are some other topics that also get talked about. Let's see. I think they talk about periodic properties. There we are. Yes. Of ionic formation. We've already kind of touched on that. And we've talked about some other topics with regard to that as well. We've talked about the electron configurations. Have we talked about electron configurations and ions? Okay. In as few words as possible, an electron configuration of an ion is simply a modification of the electron configuration of the element. And what I mean by that, for example, is here's sodium electron configuration: 1s2, 2s2, 2p6, 3s1. That's the atom. Okay. The ion, sodium plus, be 1s2, 2s2. How does it finish? You go 2p6, and then you go no más, no more. We lost the 3s1 electron. The 3s1 electron is the electron that was lost. Therefore, the electron configuration of the ion is simply one electron less. One other example. Magnesium. I'm going to do now for magnesium just a shorthand. I'm going to do neon. And remember that neon, therefore, in shorthand is going to be 1s2, 2s2, 2p6. Okay. And then I'm going to do 3s2, 3s2 for the not the ion. For the one that is not the ion, the neutral is 3s2. Okay. Looking at your periodic table, 3s2 right next to sodium. Then we actually talk about the ion, Mg2 plus. Well, it's actually the same thing as saying it is neon. 1s2, 2s2, 2p6. So the ion itself is actually the same thing as the shorthand you would use without any additional electrons. Doing a simple substitution, you see here, here's the sodium electron configuration, which happens to be the same thing as the electron configuration of neon. I utilized the electron configuration of neon to write this in shorthand and then stick on the last electrons that can't be substituted by neon. And then finally, if I lose these 2 electrons, it just simply is neon. Okay. All right. I can do these pretty quickly, so I'll show you guys a couple more. Okay. Let's see. Let's start with bromine. Bromine, neutral bromine. Now, neutral bromine, I will do first the longhand, then the shorthand, just to show you what I'm talking about and hopefully make that a little bit more clear. 1s2, 2s2, 2p6, 3s2, 3p6. Then, so 3p6 brings me to argon right there, okay? 1s2, 2s2, 2p6, 3s2, 3p6 brings me to argon. 4s2, right there, potassium, calcium, 4s2. Now, through the 3d10 of the transition elements, 3d10. And now, 4p, 1, 2, 3, 4, 5. 4p5. Still there, still visible. And we can even make it more visible by actually doing this a little more clearly. 4p6, 3, that does not help. Let's actually do it correctly. So 4s2, 3d10, 4p5. Okay. Now, if you guys follow me, right here, we're always going to use shorthand that reflect the noble gases. And what we do is we utilize the noble gas configuration from the previous line. Okay, so that would be the closest noble gas to bromine, not going forward, is argon. Follow with me. What is the electron configuration of argon? The electron configuration of argon is 1s2, 2s2, 2p6, 3s2, 3p6. Done. That is the same thing as this right here. Okay? Which means that shorthand, you can write this as argon up to that point, and then 3p, it should include 3p6, my apologies, including 3p6. So getting this right, everything up to 3p6 right there, as you can see here. And then finally, the last bit, 4s2, 3d10, 4p5. Okay. Now, on the exam, you may be asked either shorthand or normal standard longhand. Both are exam testable subjects. Okay. Keep that in mind. Not just one thing is going to appear. That's why I'm showing you both and showing you where they come from. Okay. All of that aside, now let's talk about the ion and then move on to other topics. So the ion of bromine, what happens to bromine? Does bromine gain an electron or lose an electron being this close to the noble gases? What do you think? It gains. It's easier to gain when you're this close to the noble gases than it would be to lose. You'd have to lose 7 electrons to be like a noble gas, or gain 1. It's always about what is the easiest path to gaining a stable valence shell. That is, if you are sitting at 3 or less, it's always going to be easier to lose. If you're sitting at 5 or more, it's always going to be easier to gain. Okay. So gain 1 electron to become a stable anion, becoming the bromine anion. What is the electron configuration of bromine? Sorry, the bromide ion. What's the electron? Yes. What's the what would be the shorthand? Yeah, let me ask you that. So it's 4p6, which brings us to. You're absolutely right. You've said nothing wrong. What is the shorthand, final shorthand answer? Okay, let's start there. So it's now become argon, 4s2, 3d10, 4p6, completely correct. There is an even shorter shorthand. No, we have to have, if we're going to use argon, we'd have to use these. So if we're using argon, it's going to be these. That is true. If you gain an electron, you're sitting at bromine and you gain an electron, what does your structure suddenly look like? Pardon? I know I heard it. It is krypton. Fun little question to ask. What is the shorthand of this ion? If it's an anion, it's going to jump to the one to the left, to the right. If it's a cation, it jumps backwards to the one on the previous row. The shorthand of any of these guys, the shorthand of the magnesium ion, the barium ion, is just up the previous row. So barium's shorthand is xenon. Strontium's shorthand is krypton, which actually means that the bromide anion and the strontium cation have the same valence shell. And yet they are different sizes. They have the same valence shell, but they are different sizes. They have different properties. Yeah, I'm not just talking about positive versus negative charge there. I'm talking about the fact that just because they have the same number of electrons surrounding them does not mean they are the same size particle. We'll get to that. I'll explain that later. You might already know why. You might not even realize that you know why. Okay. All sorts of fun little games here. Now, does this make sense to you guys? You guys on board? Okay. That is covering a lot of the stuff that I want to talk about when it comes to ions. We've already talked ion nomenclature. I don't want to review ion nomenclature because A, you have a previous assignment on it, and B, you've got another assignment that actually contains it as well. So what I want to talk about now is chapter 4 subjects. Chapter 4 starts on covalent bonds. And actually, I kind of am lying. I'm not quite there yet. My apologies. There are a couple of things I almost forgot to mention about ionic stuff. And I do apologize. Be angry with me if you want to. It won't get you anywhere, except more stress and frustration. So really just let it go. It'll do you more benefit. Okay. So last things about chapter 3 for tonight. First, Lewis dot structures, I think, are something actually from the end of chapter 2 to begin with. Lewis dot structures show valence electrons around the atomic symbol of the element. Now, if you are at all struggling with some of these concepts, an element is kind of like a species of matter. It is the fundamental, simplest form of matter that can exist. The fundamental, smallest particle of matter that can exist are atoms. The smallest particle of matter that can exist are atoms. Subatomic particles build up those atoms, but you cannot take subatomic particles and make anything meaningful out of them other than atoms chemistry. That's a whole separate topic. We start with atoms. Atoms with different numbers of protons in their nucleus are elements. Elements have different chemical and physical properties. Okay. If you're talking about the same element, you can change the mass of the atom of the same element by adding neutrons or removing neutrons, and that does not affect the number of protons. The number of neutrons will affect the mass of the atom, but not change what element you are talking about. That's when we talk about hydrogen with a mass of 1, hydrogen with a mass of 2, carbon with a mass of 12, carbon with a mass of 14, nitrogen with a mass of 15, nitrogen with a mass of 14, on and on and on. All of those isotopes of the element have the same chemical and physical properties aside from the mass. Okay, so isotopes are atoms of the same element, therefore they have the same chemical and physical properties aside from their mass. The only thing that differs about isotopes is the mass, because the number of neutrons in the nucleus changes. I just want to make sure I emphasize that. We've also talked about ions, where you change the number of electrons. Ions can be atoms of the same element with different numbers of electrons around the nucleus. For example, iron 2+ is iron that has lost 2 electrons. Iron 3+ is iron that has lost 3 electrons. It's still iron. Same thing for lead. Lead 2+, lead 4+. You've either lost 2 electrons or 4 electrons, but you're still lead. Okay. Pay attention to those differences. They are very key, very critical. Okay. Now, Lewis dot structures show the valence electrons surrounding the atomic symbol of the element. Okay, so hydrogen has 1 valence electron, so we put 1 electron. Carbon has 4 valence electrons, so you put 1, 2, 3, 4. You start by putting an electron on each side, and then you start doubling up. If we look at the exception, there are exceptions to this, of course. There's always exceptions, but the only real exception to that in general is helium, because helium doesn't have p orbitals. It only has 1 single orbital, and therefore helium is an exception. This is an exception. In general, it's going to look like carbon. Nitrogen goes 1, 2, 3, 4, and then a 5th. Okay. If we look at something like krypton, it has 8 valence electrons. So you go 1, 2, 3, 4, 5, 6, 7, 8. Orbitals can only contain 2 electrons. That means electrons start out individually and at most can pair up. Okay, you guys with me so far? Okay. Moving on to actual dots of ions, then chlorine 1, 2, 3, 4, 5, 6, 7, 8. Like we saw before, chlorine gains an electron, so it's no longer just 7 around that. It becomes a perfect octet 4 pairs, one on each side, brackets, negative charge. Okay. Now, ions are going the anions are going to look like that. Cations, you're going to pull off whatever you need to get, for example, magnesium, which has lost its valence electrons, and therefore you end up with a 2+. Yes, it has electrons that now take the place of that and essentially has a valence shell. It hasn't lost all its electrons, but you don't show the new valence electrons because those are still inner electrons. They don't do anything now. Okay. That is Lewis dot structures. Good so far. Okay, now the last thing I want to mention is the formula unit. Talked about this before, I know earlier today, but now let's just officially make it a thing. The formula unit is the smallest whole, not how, that's not how you spell any of these words. It is the smallest whole units of ratio between the positive and negatively charged ions that result in a neutral charge, because compound means neutral. So when you write a formula of a compound, it must be neutral. So the ratio of ions between the ratio between the ions, positive versus negative, must be such that the math works out that total charge of positive counterbalances perfectly total charge of negative. Okay. We talked about that last week when we talked about drop and swap. We talked about pairing these things up in positive versus negative. It's the smallest ratio. It does not actually represent the complete structure of a crystal. It just tells you about the balance of positive to negative charged particles. Balance of anion to cation. Okay. The ratio of anion to cation. That's all it tells you. That's why we call it a formula unit. It is the smallest unit ratio between positive and negative charge. Make sense? I hope. That's why we go with sodium chloride. Sodium is a +1 charge, is a 1+. Chloride is a 1-, so it's a 1-to-1 ratio. Okay, that's why you end up with sodium 2 oxide, because oxygen is going to be a 2- anion. Sodium is a 1+, so therefore the ratio is a 2-to-1 ratio. Okay, these things are coming in as sodium plus and O2-. This thing is coming in as sodium plus. This thing as an ion is coming in as Cl-. On and on and on. That's when we get, if you combine phosphate, which is a 3-, and you combine that with aluminium 3+, the formula unit of the compound is going to be aluminium, or no, that's just going to be aluminium to phosphate. So aluminum phosphate is just AlPO4. Okay, smallest ratio is just 1-to-1. Doesn't matter that it has a 3+ and a 3-. The smallest ratio is 1-to-1. Therefore, you do not put 3 of each. You put 1 of each. Okay, that's important because it is a common mistake to make amongst introductory and general students to think, well, the 3 charge, so let's just do drop and swap, and you get 3 to 3. If you're going to use drop and swap, you must also look at the smallest ratio. If you get a ratio of 3 to 3, you reduce that ratio to 1 to 1, and you do not write the ones. Okay. This is the formula unit. Aluminum phosphate. Also, note the standardized form of how we write and name these things. Cation followed by anion. Cation, anion. Cation, anion. Positive, negative. We always deliver the bad news, always deliver the good news and then the bad news. You don't get a choice in that. It's the positive followed by the negative. That's standard form. Okay. You always write and name cation followed by anion. Okay. And that is finally, I'm stopping, cutting this off here. This has gone on way too long. Way too long. Okay. I didn't even want to spend an hour on chapter 3, and I already did. So we're stopping here. Are there any other questions? Actually, I know there weren't really any questions. Are there any questions? Let's try it that way. Are there any questions? Okay, if there aren't any questions, then now we're jumping truly, honestly, and I'm not going to erase it. Here, we're jumping to chapter 4. This is covalent bonds, molecules, and a whole lot of other stuff. There's a whole lot of other stuff in that chapter that is important, but that is some of the biggies that jump out, that kind of define what this chapter is. So, to begin with, what's the big deal about covalent bonds? We talked about ionic bonds. Ionic bonds are the transfer. Ionic bonds are bonds between ions. Ions form by a full transfer of electron from the thing becoming the cation to the thing becoming the anion. Full transfer of electrons to be able to form ionic bonds. The reason I emphasize that is covalent bonds are bonds formed between atoms by sharing electrons. This is not a transfer of electrons. One of those biggest differences between a covalent bond versus an ionic bond is the fact that there is no transfer. Okay, so we're talking about sharing of electrons now, no longer transferring. Okay, that's a big one. This also involves something called a molecule. What the heck is a molecule? A molecule is a group of atoms held together by with ionic bonds. We end up with ionic compounds held together by ionic bonds. Okay. With covalent bonds, you end up with molecules, discrete units that are defined by their composition and are held together by covalent bonds. And they have a specific finite size, a molecular substance. A molecule has a finite size. A molecule has a finite size. An ionic compound does not. Ionic compounds will get as big as the ions available to form them, versus a molecule will not. A molecule will stop at the predefined structure. Okay. Water is always H2O. Sodium chloride, as big a crystal as you can form. Water molecule is always H2O. So, what does this mean? Well, in general, ionic compounds, and therefore ionic bonds, if we're talking about monoatomic cation and monoatomic anion, what this means is this is usually, almost always, a metal. Could be main group metal, could be transition metal. And on monoatomic, this is usually, almost always, a non-metal. Remember that the metals and non-metals are divided by that little staircase that runs right here, starting at boron, silicon, arsenic, tellurium, so on and so forth. Okay. Non-metals are these guys right here in the little corner next to the noble gases. Everything else is actually typically considered a metal or resembling a metal. There are a lot more metals than non-metals. We can go on and on about this, okay? In general, we're talking about positive versus negative, typically metal versus non-metal. If we're talking about polyatomic, there are different ways of talking about this, but you guys get the general idea, okay? When we're talking about covalent bonds, covalent bonds are typically between non-metals. And I say typically, the majority. I can't even say 99% are between non-metals, but I can say the vast majority. We're saying far more than 50% are between just non-metals. Just that little group right up in here, the vast majority of covalent bonds. And we actually generally ignore the noble gases for a lot of part. You can actually form bonds with some of the noble gases, but we're talking about really just this little group form the vast majority of covalent bonds. When I say that too, of course, that means metals are capable of forming covalent bonds with non-metals. That can happen. Okay. It's typically between non-metals, but you can get metal, non-metal covalent bonds, and there are some very important ones. For example, something you guys probably care about, hemoglobin. More specifically, the heme in hemoglobin is actually a organic metal, an organometalloid structure that starts with iron at the center, forming bonds to nitrogen. Covalent bonds, not ionic bonds. There's a lot more to it. It's very interesting. But at the center of every molecule of heme is an iron atom. Absolutely essential to carrying the oxygen throughout your entire body. That's why you need iron. That's why people who are iron deficient are anemic and therefore lower in energy. Okay. Anemia has, of course, other side effects, but one of the primary ones is lethargy. And that is not the person's fault. That's being caused by the fact that they don't have enough stuff, or your body's not properly processing it to be able to carry oxygen as efficiently to the rest of your cells. So they aren't functioning properly. Covalent bonds at work. Okay. So the thing that I'm trying to get across here is covalent bonds, a simple idea at first, and in some ways sound much more simple than transfer of electrons. Just sharing electrons, that's all, just sharing. Much more to it, okay? Let's see, blah, blah, blah. There's a whole lot of things about this, okay? Key differences, and you guys will, you'll see this in the study guide, because I'm literally just looking at the study guide as I flip through this and talk to you guys. Okay, I wrote the study guide for a reason. Yes, it's a resource for you, but I'll be honest, it's also my notes. Okay, it contains a lot of the essential components of what I want to convey to you. One of the things about ionic bonds versus covalent bonds that is so important is that ionic bonds, like I've said, involve electron transfer. Covalent bonds do not. It's that sharing of electrons. The basic structural unit of the covalent bond is the molecule. I've said that before, I'll say it again. The molecule is a finite unit. Ionic compounds, the size is not defined by the number of atoms exactly. It is whatever is available to form that structure. You can keep repeating that ionic structure as long as you have ions available to do so. All right, so let's talk about the simplest molecule that can form. What's the simplest molecule that you can form? Pardon? You need more than one atom. So you'll need more than one atom. What is the simplest atom? Pardon? So H2O is a molecule. It involves 3 atoms. You don't have to look away. You can look. Guys, you will always have a periodic table up here in the very least. The periodic table will always be in that corner. What's the simplest atom on there? It's always going to be the one in the number 1 spot. Okay, it's hydrogen. So the simplest atom, you can't get more simple than hydrogen. Hydrogen is a single proton surrounded by a single electron. You cannot get more simple than that. That is the most simple atom. Hydrogen, single proton, single electron. There's not even a neutron. If you talk about the isotopes, yes, H and a proton in the nucleus. Yes, tritium has 2 neutrons in a proton, but the most stable form, the most common form of hydrogen is a single proton surrounded by a single electron. We haven't even got a neutron in there. There's not even a neutron in there. So you've got hydrogen. Its Lewis symbol looks like that. If we talk a little bit more, okay, we could pretend that the electron density around the nucleus looks like that. Let's put another H atom there, because that's the next thing. Let's just pair 2 H atoms. Let's bring them in close contact to one another. A covalent bond means the sharing of these 2 electrons shared between 2 H atoms is the simplest molecule you can make. Because remember, a molecule requires covalent bonds. We're not talking about an ionic compound here. We're talking about a molecule. So therefore, we need to be sharing electrons. The simplest thing that could share electrons is 2 H atoms. Okay. So that brings us then to what that molecule actually looks like. You end up with the nucleus of 1 H atom and the nucleus of another H atom, now surrounded by a shared electron cloud, and the electrons will tend to spend a little bit more of their time between the atoms. They don't spend all of their time between. They still surround both atoms, but they spend some of their time close there, and now there is a bond between these two atoms. The bond is this space now, well, the bond itself is actually the space occupied right here in between, okay? Another way to look at this is H there, Lewis dot structure, pair of electrons now to be shared, giving you the hydrogen molecule with the electrons now shared between them. This would be Lewis taking two H atoms and forming the H2 molecule. Okay. Good so far. Any questions? Any concerns? Okay. So that is, to begin with, the general idea. That's now the first covalent bond that we formed. We talked about the first molecule. It gets a whole lot more interesting from there. Okay. So, any questions? All right. First thing we can do is look at covalent bonds and our periodic table. Predict the number of bonds, covalent bonds, an atom of an element might form. This goes back to valence electrons. This goes back to the octet rule, trying to form a complete octet. Yes, there were exceptions. So what you have to ask yourself is, how many electrons does the atom need to share in addition to its own to get an octet, ignoring the exceptions? Now, let's keep it simple to start with. We'll talk about octets. We won't talk about exceptions yet. We'll just talk about octets. Pretend like all we're concerned about are octets. Now, we'll go even one more step easier than that. We're just going to talk about nonmetals. Okay. Look at your periodic table here. First off, ignore, for simplicity, ignore metals. And basically what we're going to do is ignore the exceptions. So Ignore metals. Ignore hydrogen. Oh, wait, why are we ignoring hydrogen? Hydrogen doesn't need an octet. Hydrogen just needs 2 electrons to be satisfied, to be at peace. So hydrogen is actually an exception to the octet rule. It does not need an octet. The other big exception is boron. Boron is an exception to the octet rule. We'll come back to that because right now we're ignoring the exceptions. Okay, so we'll start with carbon. Carbon, an atom of carbon has how many valence electrons? Look at your periodic table. How many valence electrons does carbon have? Pardon? 4. You got 4 valence electrons. Okay. Got 4 valence electrons, therefore needs how many more electrons? Needs 4 more valence electrons. That means it's going to form how many bonds? Or how many connections? Wants to share 4 more electrons. And I specify in that way because there are different ways of doing that. Come back to that one. Just think about this for a second. Carbon needs 4 more electrons to reach an octet. Therefore, it wants to share 4 more electrons with other atoms in some fashion. Okay. Next, we'll just start with that first row of the periodic table after boron. Nitrogen has how many valence electrons? It should be 5. Okay. Carbon had 4, nitrogen had better have 5. Needs to share 3 more to reach an octet. So therefore, it's going to find ways to share 3 more electrons. That's what it's looking for. Oxygen has 6 valence electrons, needs some way to share 2 more electrons. You can see how this is going forward, right? Fluorine has how many valence electrons? 7. Therefore, it needs to share how many electrons with another in some fashion needs to share how many more electrons? Just 1 to make that 8, the octet. Okay, good so far? All right. That's why I'm showing that pattern. You see it building up. Now, the octet rule therefore means if we're going to apply the octet rule, silicon will do the same thing that carbon does. It just needs 4 more electrons shared in some fashion because it already has 4 valence electrons. Phosphorus, theoretically, following the octet rule, will have 5 valence electrons. That is 100% accurate. It will always have 5 valence electrons. Theoretically, only needs to find 3 more ways to do it. I say theoretically because the exceptions start appearing once you leave that first row. Carbon, nitrogen, oxygen, fluorine are the only things that actually obey the octet rule perfectly and never break it. There are more exceptions in reality than there are not. That doesn't mean that the octet rule is useless, because even though phosphorus has exceptions to it, sulfur has exceptions to the octet rule, they generally follow the octet rule. Their exceptions to the octet rule are rare versus common. The octet rule is a rule for a reason. It is a stereotypical behavior. Okay? It is a majority behavior. It is not a always behavior. It's a most of the time behavior. Okay? So by that same case, though, phosphorus, whoops, that's not very useful. Phosphorus, 5 valence electrons. Sulfur, 6 valence electrons. Chlorine, 7 valence electrons. Therefore, Three electrons need to be shared, 2 electrons need to be shared, 1 electron needs to be shared. In general, you'll find that rule. For the halogens, just need 1 electron. Okay. For oxygen, sulfur, selenium, 2. Nitrogen, phosphorus, 3. Carbon, silicon, 4. Why am I doing this? Well, because again, remember these are the non-metals. I'm talking about non-metals. There are very few non-metals. Okay. Questions about where we are right now? Okay, so that's using the periodic table to predict things. Beyond that, let's talk about the multiplicity of bonds. Because of course it can't be simple. It can't just be all single bonds. You can't just have one bond between each atom and that's it. Oh, of course not. Single bonds do exist, absolutely. And there are a ton of single bonds. Single bonds are a bond between atoms sharing a single pair set bonded of electrons. A bond between electrons is a pair of electrons because you can only have 2 electrons hanging out together at a time in general in an orbital. Okay. But you can have more than one pair of bonded electrons between 2 atoms. So single bonds, classic example of single bonds: carbon, hydrogen, 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 hydrogen. I've just actually drawn for you what's called a Lewis structure. I skipped over how to do that. I skipped over a whole lot of stuff to get to that. But I'm trying to just show you the individual bonds. The single lines are the bonds. Okay, there's a lot going on there. Let's unpack it. Okay. So, to begin with, bonds forming we can do as Lewis dot structures. So carbon 1, 2, 3, 4, and then 4 hydrogen atoms hanging out around it. And we'll pair up these electrons, pair up these electrons, pair up those electrons, and pair up these electrons to get this dot structure, the molecule, like so. This has a couple of different names. You could call this carbon tetrahydride, which is the binary molecular name for it. You could also utilize the organic chemistry name for it, methane. This is the structure of methane gas, natural gas, that we burn all the time. CH4, carbon tetrahydride. It's the same thing. It is also, by the way, odorless. It has no smell to it. People often think that it has a scent, but the scent you smell when you smell gas is actually hydrogen sulfide. That kind of rotten egg smell is due to the sulfur additive in methane gas that we add to protect you from suffocation, because you would never be able to smell the methane gas by itself. You add the hydrogen sulfide to it to go, Oh, wait, something doesn't smell good. That might be gas. I should probably get out of the room and not suffocate. That's a good thing. But without the added no odor. Okay. That rotten egg smell, again, that's added to it. This is the Lewis dot structure of methane. We can actually do now what's called a standard not dot structure, the Lewis structure. And what you do is you replace a paired dot like that, which represents a bond. So that's a bond. A single pair of dots like that represents a bond. For a Lewis structure, you replace the dots with a line. So instead of using a pair of dots representing the pair of electrons, you use a line to represent the bond between the atoms. Okay. And what does that look like? Well, we go from this thing. I know I'm going a little fast. That's why I'm recording it. Okay. This thing, this is the dot structure. We go to just the standard Lewis structure. Line between atoms. Line, line, line. The line will be pointing between them. The line represents a pair of electrons. Okay. The dots are a bond. Therefore, pair of electrons can also be represented with a line. That line still represents the pair of electrons. Okay. It's now the bond, which is still a pair of electrons. Any questions? Question? If there's only one dot, it's not between atoms. It's a good question. And there won't be a line because you need a pair of electrons to form a bond. Absolutely. So that brings me to an example of that. Let's see. Yes. Well, that actually takes us to Lewis structures. There are so many different directions I can go in this. Trying to follow the study guide, therefore, is the best organized way I can do it. Kind of following the book, following the study guide, et cetera, because they are linked units. I'll come back to that. Okay. Now, returning to this whole idea of multiplicity. Okay. What is a double bond? A double bond is two bonds between the same atoms. A double bond is like the name implies, double meaning two bonds, but it's still also a single double bond, just like a street between two locations can have one lane or two lanes, and it's still a single road, but it can have one lane or two lanes. It can be a two-lane road, two lane indicating two lanes, or a one-lane road indicating one lane. Each lane is an individual lane, but if you have a two-lane road, it's a two-lane road. It's a single road made of two lanes. Just like a double bond is a individual double bond, but contains two bonds between the two atoms. It's a difficult thing to kind of grasp at first. It's simple and yet difficult at the same time. It's one of those paradoxical things. So a single bond contains two pairs of electrons shared between two atoms. Okay. Just like a triple bond is three bonds between the same two atoms. A triple bond is three bonds, three lanes on a single road. Three bonds between the same two atoms. Okay. Does that make sense, guys? Okay. A couple of examples of this. Rather than explaining how to do the Lewis structures, I'm just going to show you them to you right now. Diatomic nitrogen is incredibly stable because it contains a triple bond. Okay. You start out with nitrogen and nitrogen, like so. And then you form three bonds, 1, 2, 3, between the two atoms, giving you like so. Question? Sorry? Oh, yeah, no, that's fine. I'm sorry you don't feel well. I hope you feel better soon. I'll do my best to post this for you. You bet. Okay. Good so far, guys? Okay. That's how we end up. So this structure here is the same thing as this. Okay. You've got 1, 2, 3 pairs of electrons. 1, 2, 3 pairs of electrons. Then you've got 1, 2, 3 pairs of electrons because those are the three bonds. Okay, in the triple bond. And maybe you're looking at the structure and going, well, what about these electrons here? Well, for an octet, you're going to have bonding electrons, but you may also have non-bonding valence electrons. So this right here and this right here, these are non-bonding valence electrons. They generally occur in pairs, which leads to another name for them. Another name for non-bonding pairs of electrons is called lone pairs. You may have seen this if you've delved into chapter 4, you may have come across this term lone pairs. You may have come across the term non-bonding electrons, non-bonding pairs. Non-bonding pairs of electrons are also called lone pairs. Why are they called lone pairs? Because they aren't being shared in a bond, so therefore they're more lonely than the bonding electrons. The bonding electrons get shared between atoms, so therefore they're less lonely. And people anthropomorphize all sorts of things. I know it's fascinating. It's so fun. It's so fun. It's so fun. Exhausted. Do you guys need a break? Okay, let's take a 5-minute break. Okay. Take a 5-minute break. Okay, so we've returned from our break. But now we're going to wind this down in as succinct a fashion as possible. Okay. There are to teach you guys how to structure that should be on the lecture site. There are many available here on YouTube, etc. So structures and so so drawing Lewis structures is what we need to talk about here. Okay.
what you start with is 1, figure out the type in the elements and number of each atom in the structure. Number 2, count up the total number of valence electrons available. This means all of the valence electrons. Okay. 3, figure out your center atom. Theoretically, it could be more than one center atom, but in general, your center atom. And place it okay. 4, pair up electrons between center and surrounding. This gives you your single bonds. 5, if unpaired single atoms exist, pair up into a multiplicity bond, a double, triple, okay? Or, we'll come back now, we'll do another one. So we start by forming our double and triple bonds that way. Single unpaired electrons break them down. And we need more time. Okay. Quickly write faster. I'm not going to read it. I'm not going to read it. Doesn't matter if you can read it. I'm joking. Okay. I know you want to be able to read your own handwriting. Number 6. Look at atoms and see if everyone who wants an octet can gain an octet by using any lone pairs, non-bonding electron pairs to form a neutron coordinate covalent bond as a double or triple bond. That's an option. This gets tricky.
Very quickly, because you're trying to satisfy the octet rule, but you can't please everyone. You know, it's that old experience in life. If you try to please everyone, you end up making everyone miserable because you literally cannot make everyone happy. It is an impossibility. It is impossible to always, in every situation, make everyone happy. It's just how it goes. It is impossible to make everyone in all situations happy. Yes, there will be some situations where you can make everyone happy. Everyone gets an octet. You get an octet, and you get an octet, and you get an octet. And no, this is not mimicking Oprah, I swear. Okay? But not everyone will always get an octet. It just can't be done. And so there will be situations where you try to give an octet and it can't be done, or you do try to give it, you go about it, you break an octet, you give an octet, and someone else ends up unhappy. It's just difficult. Doing structures, there are ways to do this more cohesively. And I have two options. I can either teach you a whole lot more dense material, which is what I'm inclined to do, of course, or I can just say, do your best to figure it out, which actually sounds like a really bad idea. Can you imagine doing that on the driving test? You'll be fine. You'll be fine. Just get in a car, left foot, right foot, just figure it out from experience. That's going to be a really good one. Insurance through the roof. So here is what we're going to do. We're going to do examples, and I'm going to tell you about something that we call, this is probably a bad idea, formal charge. Now, formal charge is a theoretical calculation. It is not a real charge. That's it. You treat covalent bonds like ion formation instead. And use this to figure out octets and structures. That's a whole bunch of bloody words that don't really tell you much. It's important, but it doesn't get you anywhere. So let's talk how you do it and then talk structures, okay? How to. The reason I went quick on that one is it was a bunch of words to tell you some definition stuff. Let's talk realistic, what we're actually doing. How to on formal charge is far more important. Okay. One, draw your best Lewis structure with lines for bonds and dots for unpaired and non-bonding electrons. Okay. Good so far? Okay. Now, the formal charge on an atom in a structure, that value is equal to number of valence electrons on the neutral form of the atom minus number of things surrounding the atom. And by things, I mean one thing equals one line, a bond, or one dot, an unpaired electron, a non-bonding electron. So either a line or a dot is a thing. You count dots and lines individually. Just line is one, dot is one. Those are the things. And this is as simplified as I can make it. This is as simplified as I can possibly make it, because believe me, there are more complicated ways of doing this calculation. This is the simplest way. I have done my best for you here. Okay, so now we're going to make it practical. We're going to use it. Okay, here we go. You guys with me? Okay, I know this is a lot. I get it, but here we go. We're going to start with something simple. Okay, H2O. To begin with, what atom do you think goes in the middle? Well, if you're not certain, look at the Lewis dot structures. Draw yourself the Lewis dot structures if you got to. Okay, there's the oxygen. Here's the hydrogen. How many, and there's two hydrogens, so draw your two hydrogens. How many bonds can oxygen form? It's got two unpaired electrons, therefore it can form two bonds. How many bonds can hydrogen form? Just one. Just one. So oxygen in the center, hydrogen, hydrogen. Now, form your bonds. And there's a failed bond for me. Let's try again. There's a bond. Oxygen, hydrogen, hydrogen, but do not forget your non-bonding electrons. The lone pairs must still be there. Now, formal charge. So, formal charge on hydrogen. The formal charge on hydrogen is number of valence electrons, 1, starting out. Okay. Minus number of things around hydrogen. There's one line. 1 minus 1 is 0. See? Simple calculation. Formal charge on oxygen. Number of valence electrons oxygen starts out with. 6. If you've forgotten, look at your Lewis structure. It tells you. Your Lewis dot structure already shows you the 6 valence electrons. Minus number of things surrounding it. A dot, a dot, a dot, a dot, a line, a line. That's 6. So 6 minus 6 gives you 0. Ideally, you want to minimize, get as close to 0 or as 0 a formal charge on each atom as you can. It won't always be possible, but your goal is 0 or as low as possible a formal charge as you can get. Okay? Good so far? Not terrifying yet? Okay, now let's do terrifying. Maximum velocity. Carbon monoxide. Wait, that's fewer atoms. Let's check it out. Carbon, 4 valence electrons. Group 4, 4 valence electrons. 1, 2, 3, 4. Oxygen, group 6. We've already looked at oxygen. 1, 2, 3, 4, 5, and 6. Okay. Good so far. Form a bond here. Form a bond a bit circuitously. There. Okay. Now, carbon. What does that look like? Well, it looks like carbon double bond not nitrogen, my apologies, oxygen. Let's actually keep consistent here. Oxygen. And we've got lone pair and lone pair. Now, start out by looking at the formal charge of this thing. And it is not going to be very pretty on someone somewhere. So here, carbon, formal charge. Start out with how many valence electrons? Well, 1, 2, 3, 4. Minus how many things? 1, 2, 3, 4. That's not so bad. That's 0. Okay. Oxygen, formal charge. Six, minus 1, 2, 3, 4, 5, 6. Okay, no problems. There is a problem. There is a problem. Yeah, I know. You want, wait, formal charge, we're good. Aha, but this is one of those situations. A red flag goes up. 2 unpaired electrons on carbon. Look at that. That is naughty, naughty. No, 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 no. If we can avoid that, we have to. If it's possible to avoid. It's not always even possible to avoid that. Does anyone know what you call a single unpaired electron? It's not a lone pair because it's not a pair. It's called a free radical. Have you guys ever heard of free radicals? Has anyone ever heard of free radicals? We're not talking about rebels that are wanting to go into some sort of war, revolutionary war. No, we're talking about molecules, atoms, electrons. Free radicals do radical chemistry. Radical chemistry is incredibly dangerous and incredibly toxic to biological systems. So you had better hope that it doesn't happen often or at all if possible. These guys are not stable. This is a very unstable structure. So what happens? This pair of electrons right here comes in and forms a third bond. Now, this is an exceptional structure. Okay, I told you carbon monoxide is deceptive. This little jerk is incredibly complex compared to what you'd expect. You end up with carbon triple bonded to oxygen, still got these electrons, now they're paired up, okay, and still a lone pair on oxygen. That comes from, now I'm showing you one of the, honestly, actually more difficult structures to do if you don't have a lot of practice with this, because this is one of those things that breaks a lot of rules. And I'm showing this to you to show you that a lot of structures actually honestly are easier than this. That's a lone pair there. That's a lone pair there. We can't have these two here. So we got to form a triple bond. Okay. This thing is actually very stable. Carbon monoxide exists. Carbon monoxide is something that you guys encounter and are at risk for because carbon monoxide is also very toxic. It outcompetes oxygen. It binds to your hemoglobin more tightly than oxygen. Carbon monoxide doesn't actually look stable if you look at the formal charge, though. This is one of those guys that breaks the formal charge in bad ways. So the formal charge here now is 4 minus 5, giving you minus 1 for the formal charge. And over here on the oxygen, the formal charge is now 6 minus 5, giving you a positive 1. But the total formal charge, if you add those two together, is 0. So therefore, this is still a stable structure. Compounds must be 0, formal charge must be 0 on the whole structure. Okay. Now, formal charge is something that is incredibly useful. I'm trying to show this to you guys, A, to show you structures, B, to show you why I like teaching formal charge in this class. Formal charge is not a topic typically taught in introductory chemistry. It's usually a gen chem topic, but I teach it to you guys because if you can grasp it, it can make these structures so much easier to do and give you confidence in your structures. Check this out. Nitrogen paired with another nitrogen, like so. And I should actually move this electron for convenience, pairing purposes, like so. Now, okay, bond there. Cool. Are we done? Can you guys see where the multiple bonds will form? Good. This is honestly one of the easiest structures to do. And you can have confidence in nitrogen triple bonded to nitrogen, 2 lone pairs. The formal charge, this just flies out like nothing else. You can have confidence in this structure based on that. You get 5 minus 5 is 0. 5 minus 5 is 0. Now, if you'd only formed one bond, you'd actually end up with 2 negative formal charges. Why? Because you'd have ended up with nitrogen, single bond nitrogen, and let's see, not quite like that, but you'd get a lone pair there, and you'd end up with this thing here, which, again, unpaired electrons that aren't even paired. Come on. See that? See that? You got to pair up electrons if they are unpaired. Okay, it's all about pairs. Let's see, other structures that will make sense. Yes, okay, so ions. Oh, we're so low on time. Okay, NO3 minus. Okay, NO3 minus means, first of all, number of valence electrons I haven't shown you because these have been easy structures-ish. This will make more sense now why you want to count. Nitrogen gives you 5 times 1 plus your oxygen is 3 times 6 valence electrons. Ion charge is important here. Ion means what? Means transfer of electron. Negative charge means gain or loss of electron. So the negative charge means gain of electron, means plus 1 electron into the total number of valence electrons. 3 times 6, 18. 5 plus 1 is another 6, gives you 24 valence electrons. Okay. Central atom is going to be, do you think it's going to be oxygen or nitrogen? It's going to be nitrogen. And one of the indicators of that is there's fewer of them. Typically, not always, but typically the thing you have fewer of is more likely to be the central atom. You're more likely to decorate the thing you have fewer of. Nitrogen in the center. You can save yourself some time by just pairing up the atoms if you want. If you start to get comfortable with these things, you don't even have to draw the dots all the time like that. Keep in mind, though, that these are pairs of electrons. So it's 2, 4, 6. Okay? You've used 6 electrons. Now, start drawing in, first on the external ones, your electrons. Let's just put 2 there. You know what? Let's even do it more generally than that. So you get the general idea, blah, 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 oxygen. So we've got 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay. Good so far? Okay. Now, two things. Even if we ignore formal charge, which we can do, does nitrogen have an octet? Nitrogen does not have an octet. Okay. Use one non-bonding pair from one oxygen to form a double bond. These, for example, like so. Nitrogen double bonded to that oxygen. Two pairs there now. Oxygen with its three pairs. Oxygen with its three pairs. Guys, still with me? Okay. Remember how we use brackets around ions of metals? We still do that here. Brackets around, and then the charge of the ion, -1. Now, formal charge. Formal charge on this nitrogen becomes 5 valence electrons minus 1, 2, 3, 4 things around it is a +1. The oxygens that did not form a double bond are 6 valence electrons originally minus 1, 2, 3, 4, 5, 6, 7 things around it. A 1 minus, or a -1 charge on the oxygen, a -1 charge on that oxygen. This oxygen with the double bond, 6 valence electrons minus 1, 2, 3, 4, 5, 6 things around it, gives you 0 there. Formal charge does even follow the rules of the ions. -1, -2, +1 is a total charge of -1 on the ion. So formal charge follows these rules perfectly. Okay. Now, polyatomic ion, which oxygen you pair up with does not matter. If you choose the top one, that's the same structure. Okay. Practice, practice, practice. Now, in 2 minutes, the topic of nomenclature. Does anyone have any questions on this? Do not be terrified yet, but study, study, study. Okay. You guys ready? Here we go. I promise this nomenclature is going to be easier. Okay. This nomenclature is very easy for the molecules that we're talking about, which are going to be binary. Okay. We're just talking about 2 elements, something like H2O, CO2, H2S, P2O5. Okay. The way you name these things is you utilize, first of all, prefixes for the number of atoms based on the subset, the subscript. You know these ones: mono, di, tri, tetra, penta, hexa, hepta. So penta, hexa, hepta. That's 1, 2, 3, 4, 5, 6, 7. Octa, nona, deca. That's 1 through 10. Okay. Water is dihydrogen monoxide. So for the first atom, if 2 or greater, add a prefix. If there's just one atom for the first atom, do not. CO2 is carbon dioxide, not monocarbon. It's just carbon dioxide. If there's two or more, add a prefix for the first atom. If there's only one, do not. Second atom, always use a prefix. And change the suffix to IDE, carbon dioxide. It's not carbon dioxygen, it's carbon dioxide. Dihydrogen monoxide or carbon monoxide. These are names you guys have heard before. I know you've heard of carbon dioxide. I know you've heard of carbon monoxide, in the very, very least. Okay. Beware the dangers of dihydrogen monoxide. That's a great video to look up on YouTube. It's very funny when you go out. It's a professor, typically from UC Davis, that goes out and interviews people in Davis about the dangers of dihydrogen monoxide, and everyone confuses it with carbon monoxide and gets really freaked out. It's very funny. Okay. See how easy this is, though? Compared to even nomenclature of ionic compounds, this is simple. Yes, there's a couple of other little things, like with oxygen, you say something like pentoxide. You do not say pentaoxide. It's pentoxide or monoxide. You combine things, okay? Iodine, it is monoiodic. It's a little bit tricky, but the really only tricky one is oxygen. Okay. Even then, it's not that tricky. If you understand ions, if ions are making sense, this is even easier. There's no transition metals to worry about. There's no polyatomics to worry about. This stuff, you already know. You already know. You already know those prefixes. I know you do. Mono, di, tri, tetra, penta, hexa, hepta. You know them. I know you do. There might be a couple you're not familiar with. Nona. It might sound like your grandmother rather than the number 9, but it even still sounds like the number 9. It has an N in it. You get what I'm saying, right? Hexa, like 6, like hexagon. Mono, single, like monopoly. Die. Exactly. Okay. These are things you guys know. Tricycle. Okay. All right. Let's call it a night. Let's go home. Let's study chemistry. Let's have fun. This is the end of the recording.